Welcome to The Explainer. Today, we're tackling the ultimate story of, well, absolutely everything. We are going to trace the entire cosmic arc, spanning all the way from the very first fraction of a second of the universe's birth, straight through to an unimaginably distant future where even time itself kind of begins to lose its meaning. It is an incredible journey, and I am so incredibly excited to guide you through it.
So, how does the universe actually end? It's a massive, existential question, right? It's something that has captivated humanity for generations. But what's truly fascinating right now, and get this, is that recent, fiercely debated scientific discoveries from just the past few months might radically flip our answer to this very question. This isn't science fiction, this is live, ongoing physics.
Okay, let's dive into this. Here's our roadmap for today. First, the cosmic expansion puzzle. Then, the dark energy debate. Third, our local cosmic fate. Fourth, 4 grand cosmic endings. Fifth, a journey into deep time. And finally, the unwritten cosmic future.
All right, part 1, the cosmic expansion puzzle, from the Big Bang to the Hubble tension.
Now, to figure out how it all ends, we kind of need to know how it started. So picture this, 13.8 billion years ago, the universe kicks off with the Big Bang. But, and this is crucial, it wasn't an explosion in space. It was an expansion of space itself. In a literal fraction of a second, we're talking 10 to the negative 32 seconds, space just stretched at an unimaginable rate. We call this cosmic inflation. Then, for the next 380,000 years, the universe was basically this blazing hot, opaque fog. Eventually, things cooled down, the fog lifted, and the very first light shot across the cosmos, something we call the cosmic microwave background, or CMB. Fast forward 13.8 billion years, and boom, here we are today.
But here is where things get weird. We've hit a massive puzzle. See, scientists have 2 different ways to measure how fast the universe is expanding right now. When they look at the late universe, using exploding stars called supernova, they get an expansion rate of about 73. But when they look at that ancient early universe CMB light we just talked about, they get 67. It's honestly like measuring a room starting from 2 different walls and stubbornly getting 2 different answers. This is known as the Hubble tension, and it's a huge deal because it strongly suggests there's some totally undiscovered physics woven into the fabric of our cosmos.
Moving on to part 2, the dark energy debate, the invisible majority.
And this brilliantly illustrates the heart of the problem. If we look at the fundamental ingredients of the universe, it's wild. Everything you've ever touched, seen, or measured, literally all ordinary matter, makes up just 5% of the cosmos. Just 5. Then, 27% is invisible dark matter, which acts like cosmic glue, pulling things together with gravity. But a staggering 68%? That is dark energy. It's this mysterious, invisible force that actively pushes space apart, and it is absolutely the dominant driver of our universe's fate. Now, scientists describe this repulsive force using a super important variable called the equation of state, which they just call W. Think of W like a cosmic gas pedal. If W equals exactly -1, it means Einstein was right all along. Dark energy is a fixed cosmological constant. Basically, it's a cosmic cruise control, pushing space apart with the exact same strength forever. But if W changes over time, wow, then everything we think we know about the end of the universe shifts entirely.
And believe it or not, this exact variable is the center of a fierce, live scientific debate right now. In 2024 and 2025, the massive DESI collaboration dropped some data hinting that dark energy might actually be weakening as the universe ages. This was a total earthquake in cosmology. But then, in June 2026, a team from the University of Southampton, which actually included the Nobel laureates who discovered dark energy in the first place, issued a pretty strong rebuttal. They argued that if you properly correct for age biases in the host galaxies of those supernovae, the evidence for weakening dark energy just vanishes, meaning the fixed constant model is still perfectly fine. The debate is wide open, and it is honestly so thrilling to watch this science happen in real time.
All right, part 3, our local cosmic fate, the Sun and the Milky Way.
Before we tackle the end of the entire universe, let's zoom in on our own neighborhood. What's going to happen right here? Well, 1 billion, that's our number. In exactly 1 billion years, our sun is going to gradually brighten by about 10%. Now that might sound pretty small, but it's enough to trigger a runaway greenhouse effect right here on Earth. It'll literally boil away our oceans and permanently end the planet's habitability. So you've got plenty of time to renew your lease, but our run on this specific rock definitely has a hard expiration date.
As for the sun itself, it'll stick around much longer, going through a pretty spectacular demise.
In about 5 billion years, it'll run out of its core fuel and swell up into a massive red giant star. It's going to swallow Mercury and Venus whole and leave Earth completely scorched. Funnily enough, this will briefly push our solar system's habitable zone way out, which could temporarily thaw out icy moons like Jupiter's Europa. But eventually, the sun is going to ignite a helium flash, blow off its outer layers, and ultimately collapse into a super dense, glowing ember known as a white dwarf.
Now, looking a bit further out in our galactic neighborhood, we have a genuine scientific surprise. See, for over a decade, textbooks have confidently stated that our Milky Way galaxy was on a totally inevitable collision course with the neighboring Andromeda galaxy. But astonishingly, new 2025 data from the Gaia spacecraft completely flipped this. By factoring in the gravitational tug of a smaller galaxy called the Large Magellanic Cloud, the models now show we might actually miss each other entirely. It's basically a 50% coin flip chance that we'll collide in the next 10 billion years. Crazy, right?
Which brings us to part 4. 4 grand cosmic endings. How it all concludes.
So, let's zoom back out to the ultimate fate of everything. Remember that dark energy equation of state we talked about? Well, the end of the universe completely depends on how that behaves. So the crucial point is that physicists generally debate 4 main doomsdays. The absolute favorite right now is the Big Freeze, where dark energy just keeps pushing everything apart forever until the cosmos goes incredibly cold and dark. But if dark energy somehow reverses, we get a big crunch, which pulls everything aggressively back together. If dark energy gets violently stronger over time, we face a big rip, literally tearing apart galaxies, planets, and eventually even atoms. And finally, there's the Big Bounce, which suggests a crunch might just compress everything enough to trigger a brand new Big Bang, an endless cycle.
Let's explore that further in part 5, Journey into Deep Time, moving era by era.
Let's assume for a second that the widely favored Big Freeze scenario is correct. Prepare to stretch your imagination here, because ordinary numbers are just going to stop making sense. Right now, we live in the star-filled Stelliferous era, but imagine looking up at a night sky where the very last star has flickered out. By 10 to the 14th power years from now, star formation will completely stop as the universe just runs out of gas. That plunges us into the degenerate era, an era populated only by dead stellar corpses like white dwarfs and black holes. Fast forward to 10 to the 40th power years, and all ordinary matter might literally decay away into nothing, leaving only colossal gravitational monsters in the void. Welcome to the black hole era. And then, we hit this incredibly humbling number, 10 to the 106th power years. That is a 1 followed by 106 zeros. That is how long it takes for even the absolute largest supermassive black holes to finally evaporate away into nothingness through Hawking radiation. Once that very last black hole vanishes, the universe enters the permanent, eternally featureless dark era. No energy, no light, just a totally diffused soup of cold, lonely particles forever.
Finally, part 6, the unwritten cosmic future. What comes next? Okay, let's snap back to the present day. What does a terrifyingly vast timescale like that mean for us, right now? Well, it means that today is arguably the most exciting time in history to be observing the cosmos. This science is fiercely alive. In the coming decade, we've got incredible new tools, like the Euclid Space Telescope, the Vera-Rubin Observatory, Sphere-X, and the ongoing Gaia missions that are going to map literally billions of galaxies. They are perfectly poised to finally solve this dark energy mystery and tell us, definitively, which of those grand cosmic endings we're truly headed toward.
When you really stop and realize that the universe could last for 10 to the 106th power years, and we are only 13.8 billion years in, it begs a pretty staggering question. Are we just living in the opening pages of a cosmic story that has barely even begun? I mean, all of human history is just a microscopic spark at the very dawn of time. I really hope this explainer leaves you just as humbled and honestly just as hungry to learn more as I am. Thank you so much for exploring the cosmic arc with me today.